All right, so we're going to collect some more examples here. So we've seen q adjoin root 2 over q. The degree there is 2. Or that's one way. We looked at a basis and such. Or an alternative way of going about this, using what we just showed, is that the minimal polynomial of root 2 over q is t squared minus 2. By Eisenstein's criterion, it's irreducible and it's monic, so it's a minimal polynomial. And this guy has degree 2. So the degree of t squared minus 2 is 2. And so this should be the degree of the minimal polynomial of the element we're adding in, and the 2's agree. So that's our first example that we've seen a bunch of times already. The minimal polynomial, so let's compute the degree again of q adjoin root 2 root 3 over q adjoin root 2, something that we already saw. We saw that this was 2, but alternatively, the minimal polynomial of root 3 over q adjoin root 2, the base field here is q adjoin root 2, is t squared minus 3. Why is it t squared minus 3? Well, we saw that the square root of 3 was not in this field. So it can't be a linear polynomial because it's not in that field. So it has to be a quadratic polynomial or higher. It turns out there is a quadratic polynomial that root 3 satisfies. It's this one. Okay. So this is irreducible over this larger field in Q, but it's still irreducible there. And it has degree 2. And the degree of t squared minus 3 is 2. And those two match, of course. Another example is something like a transcendental extension. So that's, of course, infinite as pi is transcendental. Let's do two more examples. So another example is we might try to compute the degree of something like, well, maybe we'll just do one more example. Something like root 15 and then root, let's see, 21 and then root, let's say 35 over q adjoin root 15 and root 21. And this last example is kind of cautionary. So it looks like what we're doing is we're adding a square root. So we would be tempted to say that the minimal polynomial of root 35 over q adjoin root 15 root 21 is t squared minus 35. And that's very, 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 very tempting to say, given what we've done before, right? However, we would be wrong. And what I'm trying to get at here is it's very, very important to actually check that these sort of tempting claims are actually true. Right? It's one thing to say it's true, it's another thing to do the math. So it turns out that root 15 times root 21, I can't do that in my head, but I know root 15 is 3 times 5, root 3 times 5. And I know root 21 is root 3 times 7. So there's 2 root 3s, so that's 3 root 35. 3 root 5 times root 7 is 3 times root 35. So actually, the minimal polynomial of root 35 is actually t minus root 35 over this field q adjoin root 15 root 21, because it's root 35 is in the field. You can build it with the guys that you have. So what's the degree of this extension? The degree of this extension is 1. Okay. So we do have to be careful that the elements that we're adding are actually new. We can't, we have to actually be able to do the math. Right? And you'll have an example on your homework where you're going to be computing a degree of an iterated quadratic extension like this. And if you just sort of naively say it's a certain number, it's not going to work out. So it's very important to check that every time you add something, it's new. And that's something that we did. Let's see if I can find it real quick. In great detail here with the q adjoin root 2, root 3 example, right? We really had to check that adding in root 3 was honestly new. So just be careful about that. And that'll be the last example we do here.